For more than a decade, quantum computing and AI data centers have been covered as two completely separate stories happening in two completely separate worlds. AI data centers were about gigawatts, grid strain, liquid cooling, and the relentless scramble to build enough physical infrastructure to keep up with explosive demand for computers. Quantum computing was about lab physics, cryogenic cooling chambers, and breakthroughs that always seemed to be permanently a decade away from anything commercially useful. That separation has started to genuinely collapse in 2026, and the story is not that quantum has replaced or killed AI data centers, despite what some sensationalized headlines might suggest. The real story, which is honestly more interesting than a fake death narrative, is that quantum computing is moving directly into AI data centers as a new layer of infrastructure that works alongside classical AI compute rather than against it. The clearest and most concrete evidence of this shift comes from three of the biggest names in computing making real, physical moves rather than just talking about future possibilities. Microsoft has been actively developing a quantum processor specifically engineered to fit into standard server rack footprints, meaning it is designed from the start to slot into the same physical infrastructure that data centers already use for classical computing rather than requiring an entirely separate specialized facility. IBM has gone even further in practical terms, running an actual quantum computer connected directly alongside a classical supercomputer in a working hybrid configuration. And Nvidia, the company that has defined the AI hardware boom of the past several years, just launched a family of open-source AI models called Ising specifically built to manage the error correction challenges that have historically plagued quantum hardware, marketing the combination as quantum GPU supercomputing. When Microsoft, IBM, and Nvidia are all making concrete infrastructure moves in the same direction within months of each other, that is a meaningful signal that something real is happening rather than speculative hype. To understand why this integration makes sense technically, you need to understand the specific problem that quantum computers have always struggled with and why classical AI computers are turning out to be the unexpected solution. Quantum computers are extraordinarily powerful for certain types of calculations, but the quantum bits, or qubits, that they use to perform those calculations are notoriously fragile and prone to errors caused by environmental noise, temperature fluctuations, and electromagnetic interference. This error rate has been one of the primary obstacles preventing quantum computers from delivering reliable, useful results outside of controlled laboratory conditions for years. Correcting these errors in real time requires enormous amounts of computation to constantly monitor and adjust the quantum system, and it turns out that the kind of massively parallel processing that GPUs excel at is extremely well suited to this error correction task. Nvidia's Ising models are specifically designed to use AI and GPU compute to manage and correct the errors in quantum hardware, which means modern AI infrastructure is not being replaced by quantum computing. It is becoming the support system that makes quantum computing practically usable in the first place. The timeline that industry experts are actually working with for when this hybrid quantum AI infrastructure becomes commercially meaningful is worth stating clearly, because it directly contradicts any narrative suggesting quantum has already taken over. According to analysis presented at industry events throughout 2026, quantum computing integration into mainstream data center infrastructure is expected to reach a meaningful tipping point around 2028, and fault-tolerant universal quantum machines, the kind capable of reliably solving complex real-world problems without being overwhelmed by errors, are anticipated as early as that same year at the earliest. Quantum system deployments today remain primarily lab-based, even as hyperscale cloud providers, telecommunications companies, and governments begin acquiring and prioritizing quantum infrastructure investment. This means that as of right now in 2026, we are in the early infrastructure building and integration phase, not in a phase where quantum computing has displaced or killed anything related to AI data centers. The energy and power dimension of this story is particularly important to understand correctly because it is where the most confusion and misinformation tends to spread. Quantum computing does have genuinely interesting power efficiency characteristics for certain specific calculations, with some industry analysts noting that quantum processors can require a fraction of the energy that a classical data center would use to solve equivalent problems in specific specialized domains. This has led to speculation that quantum could eventually help address the data center energy crisis that has become one of the defining infrastructure challenges of the AI boom, with single server racks now drawing power loads that have climbed from around 10 kilowatts to more than 50 kilowatts, and the most aggressive hyperscale designs quoting over 100 kilowatts per rack. But industry analysts covering this convergence have been explicit and direct on one point: quantum computing is not going to make the data center energy crisis disappear. Quantum computers excel at very specific categories of mathematical problems, particularly certain optimization and simulation tasks, but they are not a general replacement for the broad range of AI training and inference workloads that are driving the current massive data center power demand. The Open Compute Project, the influential industry standards body that includes major hyperscalers like Meta and Microsoft among its members, has been actively working on developing data center standards specifically for quantum computing integration, with officials stating their goal of having a first draft of quantum readiness certification standards available sometime in 2026. This kind of standards body involvement is a meaningful signal of industry seriousness, because standards organizations typically only invest significant effort into developing certification frameworks when there is genuine expectation of near-term commercial deployment that justifies the standardization work. The Open Compute Project's existing self-assessment program already helps data center operators demonstrate they meet best practices defined by major hyperscalers, and extending that framework to cover quantum-ready facilities suggests the industry expects quantum infrastructure deployment to become common enough within data centers to require standardized approaches rather than remaining a handful of one-off custom installations. Real estate and data center infrastructure companies have also begun treating quantum computing as a legitimate new demand category for their facilities, which is a telling sign from an industry that tends to be conservative and evidence-based about what infrastructure investments actually make commercial sense. Industry analysis describes data center demand evolving in layers over the decades, comparing it to a layer cake where each new wave of technology, from early corporate IT hardening, through the mobile application boom, through cloud computing, through the artificial intelligence infrastructure build-out, adds a new layer of demand on top of what came before rather than replacing previous layers entirely. Quantum computing is now being positioned as the newest layer in that cake, emerging alongside and on top of the existing AI infrastructure layer rather than displacing it. Data center operators are increasingly comfortable with the kind of facility customization that quantum systems require, partly because the AI infrastructure boom of the past several years has already forced the industry to rethink cooling, power distribution, and rack spacing in ways that make accommodating quantum hardware's unusual requirements more feasible than it would have been 5 years ago. The specific physical infrastructure challenges that quantum computers present to data center operators are genuinely different from classical AI compute and explain why this is described as an engineering integration challenge rather than a simple drop-in replacement. Quantum computers, particularly the superconducting qubit varieties that companies like IBM and Google have invested heavily in, require extreme cryogenic cooling to temperatures near absolute zero, dramatically colder than anything classical data center cooling systems are designed to provide. Other quantum computing approaches, like the neutral atom and trapped ion systems that various companies are pursuing, have different but equally specialized environmental requirements involving precise laser systems and vacuum chambers. Quantum computers also remain physically bulky, finicky to operate, and non-standardized across different manufacturers compared to the relatively interchangeable server hardware that classical data centers are built around. This is precisely why Microsoft's effort to fit a quantum processor into a standard server rack footprint is significant. It represents real engineering work to make quantum hardware compatible with existing data center physical infrastructure rather than requiring entirely bespoke facilities for every quantum deployment. The commercial use cases that are actually driving this quantum AI data center integration matter for understanding why companies are investing in this convergence right now rather than waiting for some distant future. Quantum computing shows particular promise for specific categories of problems including complex molecular simulation for drug discovery and materials science, certain types of financial portfolio optimization, logistics and supply chain optimization problems with enormous numbers of variables, and specific machine learning training tasks that involve searching through vast combinatorial possibility spaces more efficiently than classical computers can manage. None of these use cases represent a replacement for the general-purpose AI training and inference that dominates current data center workloads. Instead, they represent specialized capabilities that organizations running AI infrastructure want to have available as an additional tool, which is exactly why integrating quantum processors into existing AI data center facilities rather than building entirely separate quantum-only facilities makes practical and economic sense for the companies pursuing this strategy. Forbes and other industry analysts have made bold predictions about quantum computing reaching what is called quantum advantage, the point at which it becomes economically or technologically preferable to use a quantum solution over the best available classical computing alternative for an important real-world problem, with some predictions suggesting this milestone could be reached as early as 2026 itself for specific narrow applications. Whether these optimistic timelines prove accurate or end up being pushed back as quantum timelines have frequently been throughout the technology's development history, the broader trend of quantum hardware moving out of pure laboratory contexts and into commercial data center environments is happening now, documented through concrete infrastructure investments from major companies rather than remaining purely theoretical. This represents the kind of measured, evidence-based technological transition that deserves genuine attention and understanding rather than the exaggerated death and replacement framing that tends to attract clicks but misrepresents what is actually occurring in the industry. For anyone working in or following the data center and AI infrastructure industry, the practical takeaway from this quantum integration trend is that the skills and infrastructure investments being made for AI right now are not at risk of becoming obsolete due to quantum computing displacing them. If anything, the opposite is true. The GPU compute, the AI software expertise, and the data center infrastructure that the AI boom has built over the past several years are turning out to be necessary components for making quantum computing commercially viable at all, given how central AI-driven error correction has become to the entire quantum computing value proposition that companies like Nvidia are now building products around. The relationship between these two technologies is fundamentally collaborative and complementary rather than competitive, which is a far more accurate and frankly far more interesting story than any narrative suggesting one technology has killed or replaced the other. The bottom line on quantum computing and AI data centers in 2026 is that we are watching the early stages of a genuine technological convergence, with real companies making real infrastructure investments on a timeline that points toward meaningful commercial impact starting around 2028 rather than anything that has already happened or is happening right now in a dramatic, headline-worthy way. Quantum has not killed AI data centers. Quantum is moving into AI data centers, learning to lean on AI computers to solve its own fundamental error correction challenges, and positioning itself as the newest layer in the ongoing evolution of data center infrastructure rather than a replacement for what came before. That is the real story, and it is worth understanding correctly rather than through the lens of an exaggerated claim that does not reflect what is actually happening in the industry. Right now,